Hey everyone, thanks for joining us. I'm Yotam. I'm CEO and founder in TensorLeap. At TensorLeap, we help STEAM AI teams to understand why their model fails and how to fix it. We're building applied explainability platform, focus on the model debugging and active learning. One of the biggest problems in AI in production in real environment today is not accuracy. It's not aggregated metrics. Is specific subsets where the model tends to fail. Super difficult to detect them, to understand why that happens and how to tackle it. Today webinar is all about error slice detection. We did some extensive work internally on how to do that in TensorLeap, and our fellows here, Amit Cohen and Tom Coren, is going to lead the webinar today. They having hands-on work on how to improve those methods. So without further ado, I will deliver the focus to Amit Cohen, our researcher, and Tom Coren, our head of AI. Guys, it'd be great if you could introduce yourself and take it from here.
Great. Hey everyone, I'm Tom. I'm head of AI here in TensorLeap. Today, Amit is going to talk a lot about some research that we've been doing in TensorLeap and share with you some of the conclusion with respect to error slicing. I'll be here answering questions and walking you through this road. And Amit, please give a short intro about yourself as well.
Yeah, thank you, Tom. So my name is Amit Cohen. I'm a scientist at TensorLeap, and I've been working and researching for the past couple of months the domain of error slice detection, and I'm going to present the webinar today. So I think we can start, right? So let me share the presentation. Okay, I assume you all see the presentation. The subject of the webinar today is error slice detection, identifying critical failure modes in deep learning models. We have a lot on our plates today, so let's just start. A quick agenda. We'll start with talking about motivation and why is this problem interesting. We'll define what an error slice detection algorithm is. We'll talk about evaluation of those algorithms. We'll deep dive into two methods. We'll discuss problems with these methods. We'll briefly discuss about solution to those problems, and we'll finish with takeaways. So imagine you train a model, you validate it, you test it, everything looks amazing, you deploy to production, and then you start seeing frequent failures. What would you do? What would be the next step? An ad hoc solution could be manually analyze and try to find error patterns in the data. The problems with it is that first, it doesn't scale. Second, it doesn't generalize. You may be able to find small portions of the problem, but you will probably not find the entire problem. And it is biased towards what you think the problem is. So overall, it's not a very good solution. Another ad hoc solution could be labeling more data and train your model with this new data. The problems with it is that, first of all, it can be very expensive and inefficient. And second, it will just probably not solve your problem. So I'd like to suggest a different approach, which is finding coherent error groups in a systematic way. And I claim that this is a step towards solving your problems in production. So why is detecting coherent error groups in a systematic way a step towards solving your problems in production? First of all, errors are systematic and they are not random. Aggregated metrics hide consistent failures on data subsets. Those subsets are called in the literature error slices or aggressors. And the problem is that you can see excellent results on aggregated metrics like test accuracy, for example, but you are not aware of the underlying error slices that may be in your data set, and those subsets are often critical. And by having a list of error slices, you can enable more robust models, more trustworthy models. You can prioritize your fixes, and you can optimize your R&D efforts. And I'd like to back it up with some examples. So in the autonomous vehicles domain, you may be working on fixing minor issues with your model, while your model consistently fails to detect pedestrians in rain, which is clearly a more urgent problem that you would probably want to prioritize if you would know it exists, but you may just not know it exists. A second example would be in the fraud detection domain. You may be experiencing a lot of false positives, so you work on improving your overall precision of the model, while you consistently miss frequent fraud patterns, which is, again, a more urgent problem that you may not be aware of. So the conclusion is that systematic aggressor discovery is essential. It's not just nice to have. What is an error slice detection algorithm? How do we define it? So the input to an error slice detection algorithm would be a labeled dataset plus an optional trained model. The objective of this algorithm would be to detect coherent underperforming subsets in the labeled dataset. Those subsets, as we said, are called error slices or aggressors. And as an output, it outputs a set of distinct error slices. What is a good error slice detection algorithm? A good solution will recover most of the systematic errors. It will recover them with high precision, meaning it will not return a lot of false positives. It will group errors in a coherent way, and those error slices will be interpretable by domain experts. A key question that raises now is, how do we measure success? It's not that straightforward. In order to measure success, we need an evaluation protocol, and the first thing we need to do is define GT slices. We need a data set with known problems, so we can compare our error slice detection to our error slice detection algorithm to the GT. So literature defines several types of GT error slices. One of them is a correlation error slice. For example, if your task is predicting whether an image contains an airplane or not, a correlation error slice can be created by having airplanes in the training data only with a sky background. And then in test, the error slice will contain a group of samples that have airplane with different backgrounds. The model is likely to learn that airplane equals sky, and it will probably fail on the error slicing test because it is out of distribution for it. So we take this type of error slice, and we take several others, and we create a data set that contains some known problems and mostly non-aggressor data. And we run the error slice detection algorithm, which outputs a set of distinct predicted error slices. We then take each GT slice and find the best match out of the predicted error slices, just like in object detection bounding boxes. For each GT, we find the most overlapping predicted error slice. And we measure success by using a metric called precision at K, which measures out of the top K samples in the predicted slice, how many of them are in the GT slice. So we have our GT slice, we have our matched predicted slice, and out of the top K samples in the predicted slice, how many of them are also in the GT slice. And higher precision at K probably means a better alignment between precision and GT. So given this evaluation protocol, we are ready to talk about methods for error slice detection. So we will see two methods today. They are called Domino and Facts, and let's start with Domino. So Domino, discovering systematic errors with cross-model embeddings. This is a paper that was published in ICLR 2022 by a group from Stanford University. And this is a pioneering work in the domain of error slice detection. And I'd like to explain the method with an example. But first, let's talk about the settings of the problem. The inputs is a labeled data set and a trained model. And in the example here, the task is determining whether an image contains a bird or not. And we can see that some images have birds in them, some do not. But all images with birds are with a sky background, but there's also sky images with no birds in them. As we saw earlier, the model is likely to learn that sky equals birds, and thus it is likely to have low performance on sky images with no birds in them. Given those settings, let's explain their method. Their method has three stages: embed, slice, and explain. In the embed stage, what they do is take the entire data set and embed all the samples using a clip image encoder. And they then concatenate two things to each vector. The first is classification GT label of the sample, and the second is the logits of the input model on the sample. So now each sample is converted into a vector that contains clip encodings, GT label, and logits. They then splice the data into clusters using Gaussian mixtures model, and they return the worst performing clusters as error slices. We can see in the presented example that the method was able to detect the sky error slice, and it is separated from the birds with sky just as it should be. This is a correct error slice detection. And their last and third stage is explain. We said earlier that a good method is interpretable, and to make their method interpretable, what Domino do is it creates a textual description of each error slice, and they do it by utilizing the fact that CLIP is a cross-modality model. They encode a corpus of text phrases into the same latent space as the images, and then for each error slice, they take the closest textual phrase in the latent space and make it the description of the slice. We can see in the example that the error slice got the correct description, which is sky in that case, and this is a good result. Now I'd like to present a visual result from the paper. The task here is determining whether an image contains a vehicle or not. And this error slice is of a different type than the one we saw earlier. This is called a rare error slice. To create it, they take the submarine subclass, which is, they take the submarine, which is a subclass of the vehicles class, and they almost completely remove it from training. Then when model sees it in test, it is likely to fail on it. I'll repeat it because it's a subtle point. The model does not know what a submarine is. The submarine is just a subclass of the vehicles class. And the model barely sees submarine samples in training, but there's a group of submarine samples in test, and this is the error slice. The result we see here is an error slice that Domino has detected. We see some representative images. We see that the error slice is coherent. Those are all images of a submarine, and the description is informative, a photo of a submarine. This is a good error slice detection by Domino. Now I'd like to go to the next paper, which is a follow-up work to Domino, and it is called Facts. Their title is Facts, first amplify correlations, and then slice to discover bias. This is a paper that was published in ICCV 2023 by a group from Georgia Institute of Technology. And again, I'd like to explain the method using an example. And again, I'd like to start with defining the settings. So the input to facts is only a data set, and the task is determining whether an image contains an airplane or not. And we can see that the dataset has bias. Airplane examples are mostly with sky background, but there's a minority of airplane examples with different backgrounds like water or land. Yeah, so given those settings, let's discuss their method. So basically, facts is just like Domino, but instead of having an input model, they use a weak model that they train that they create by training with high regularization. This weak model will probably learn the easiest connection it can find, which will be in that case that sky equals airplanes. They then utilize this weak model, and they are able to separate between easier examples and harder examples. Technically, in the first stage, they are training this weak model again by using a high regularization. And in the second stage, they do exactly what Domino does, but with this weak model, with the logics of this weak model instead of the logics of the input model. And we can see in the example that Facts was able to detect coherent slices that indeed separate easy samples from harder samples. This is a visual result taken from the Facts paper. The task here is determining whether an image contains a bird or not. And the bias in the dataset is that birds mostly appear with a grass background. The error-slice prediction that Facts produced is compelling. We have several slices. Each of them contains different background. We have birds with a water background, birds with sunset background, and birds with trees background. They are all coherent, and the model indeed fails on them. So this is a good error-slice detection by Facts. And this basically wraps up the Facts method and the two methods that we're going to see today. I'd like to discuss now about weaknesses of those methods. So there are several gaps between those methods to practice, and I'd like to discuss just some of them. First is that they are designed only for classification, and we know that there are more tasks out there. Second is that they are highly sensitive to hyperparameter tuning, and a small tweak can lead to a very different results. And this is not robust, and this is not a wanted behavior. Third is that precision at K might not be enough for real-world applications. In the example, we can see the left prediction is probably better than the right prediction, but the right has a higher precision at K. So we may need to come up with different metrics in order to determine whether a prediction is good or not. And last, different latent spaces can be used to detect different types of problems. For example, one latent space can be used to detect slices of blurry images or noisy images, and another latent space can be used to detect birds with a sunset background, for example, something more semantic. To bridge this gap, we came up with several suggestions. I'd like to briefly discuss about them. So we can go beyond precision at K and define more metrics to evaluate an error stress detection algorithm. We can define coverage, which measures how much of the total GT aggressors are captured. The green area here is the captured or covered GT, and the red area is uncovered GT. And clearly we want a higher coverage. Another metric we can use is max IOU, which measures what is the maximum overlap between predicted error slices and GT slices. The green area here is the max IOU, and clearly higher max IOU probably means better alignment between prediction and GT. We can do different stuff like smart pre-processing. In the example here, we can see that the prediction is noisy. We have a lot of false positives, and the clustering is not the best. We can remove samples that perform well, and by that help the error stress detection algorithm to produce cleaner and better results. And lastly, we can use multiple latent spaces. We said earlier that different latent spaces can be used to detect different types of problems. So we can aggregate error slices over multiple latent spaces and thus get better results. So the takeaways that I would like you to leave this seminar with are first, model failures are systematic and they are not random. And if you rely only on aggregated metrics, you can miss critical issues. Second is that having an effective method for error slice detection can make you trust your model more. It can lead to fewer production failures, and it can lead to much faster and more focused R&D. And last, you can start detecting error slices today. Methods like Domino and Facts and more are public, they are reproducible, and their code is available online. So I encourage you to start doing it. And with those takeaways, I'd like to finish and give you the opportunity to ask questions. And thank you for listening.
Hey, Amit, thanks a lot for this talk. It was super interesting. Everybody who currently attends, there's a Q&A button in the bottom. Some people have already asked some questions during the webinar, but if you have anything you want to ask, feel free to just ask a couple of questions. We'll now answer some of them. So, Amit, I see some people are interested in data sets. How do you actually, what are the current ways to evaluate it? Are there some off-the-shelf data sets we can use to just check this? Maybe you can share a bit about that.
And yeah, so the papers depict some of the data sets that they use. There are some data sets like Nico, for example, which is a very good recommended data set to work with. There are some synthetic data sets like Waterbirds, for example, and Domino, which is a pioneering work in the domain, as I said, came up with a data set of their own. So I would recommend go with the existing data sets like Nico++ and Waterbirds. I'd start there and build my way up from there. You're muted, Tom.
Can you hear me?
Yeah.
Yeah, I was just wondering, you described two things. You described synthetic data sets and real data sets. Do you feel that Domino and the other papers have a difference between them? Is it really easier on synthetic? Is it noticeably easier on synthetic?
Specifically, the synthetic data set that they report their results on is a very toy example. It's Waterbirds is a very toy example. It has only two classes, land birds and water birds, and it has two contexts, which is land or water. and the model is trained with water birds on water and land birds on land, and the aeroslice is the opposite, is the water birds in different contexts, or land bird in different contexts. I would say that it's hard to measure what exactly make it easier, whether it's the synthetic, is the fact that it's synthetic, or the fact that it is very easy. I would say I would recommend start with the waterbirds, just to sanity check your aeroslice detection algorithm, and then go to a more complicated data sets. That would be my recommendation.
That's great. That's great. I've seen another question that I want to raise. So I see someone asked maybe to share a bit more about how can multiple latent space be used to better detect errors. So maybe you can give like a more concrete example. Say, I don't know, I'm doing action recognition and I have some errors that has to do with the temporal motion, and I have other errors that has to do with like the semantic of the scene, of the location. How can I actually go about separating the two and solving them in two distinct spaces?
So I would say different latent spaces can represent different features and different semantics. I think, for example, you would probably want to create a latent space that contains temporal information. Probably want to aggregate somehow your latent space over the video or your sequence. And you will probably want to, as I said, create a latent space that contains temporal information, and you'll be able to utilize it in order to find context in the temporal semantic. Does it answer the question?
Yeah, I think that's perfect. And I see we have a follow-up on that. Like people are asking if we have a paper or reference for this idea. So it's part of a research we're actually being internally doing, and I encourage everyone to reach out. I don't have a reference in hand, but we can definitely discuss it. We benchmark this internally across multiple lane spaces, and we have some surprising results. So feel free to reach out and discuss this with us. One other question that I'm seeing is, you mentioned something about smart pre-processing. So maybe you can give us some motivation as to why, if you remove some of the, if you have a pile, some samples are really good and you remove them from the problem, why does that make error slicing detection better? How does that help?
As you said in the question, you already use a prior that you have. You will probably not want to have good examples as an error slice, as a detected error slice. So you can help your algorithm by removing those samples and only let it detect error slices within this filtered latent space, I would say. It lets the algorithm to focus on the real problem and find patterns there, instead of having a lot of noisy information that basically does not help it. So this is a big step towards improving the results. We did ablation tests there, and we saw that this significantly improves our results. Yeah.
Thanks for that. Any other questions? Feel free to ask them in the Q&A.
Okay, guys, thank you so much for joining us today. We are looking forward to seeing our next webinar. Probably in about a month from today. We'll share some more details in the coming few days. Amit, it was brilliant. Your work here is super interesting. I'm always curious to see what your team is doing here. And see you soon.
Thank you very much. And thanks everyone for listening and